Part 11 of mathematical physics. In this video we discuss about calculus of residue. The calculus of residues. Residue at a pole. F of z is equals to summation a n z minus a raised to power n plus summation b n z minus a whole power minus n equals to 0 to infinity. Here n equals to 1 to infinity. Here an equals to 1 by 2 pi iota integral of closed surface contour C fz divided by z minus a whole power n plus 1 dz, and bn is equals to 1 by 2 pi iota integral of closed contour f of z dz divided by z minus a whole power minus n plus 1. Here this C represent circle enclosing a and b other singularity. Z minus a mod is equals to r. Here for value of n equals to 1, bn is equals to this fz dz. Here this b1 is called residue of fz at pole z equals to a, and represented this residue z equals to a equals to b1. This is one method finding residue. Now another method for finding residue. Method of finding residues. First method is residue at simple pole. Here if fz has a pole at z equals to a, then residue of fa equals to limit z minus a fz. Here this is limit from z tends to a. Here f of z now residue at simple pole is second. For now residue at z equals to a is equals to phi a divided by psi dash a. Here if we put z equals to a on the denominator value, it becomes, for this case if we put psi z in the psi z, z equals to a, psi z become 0. This condition is used for in this type of case. Now second method, residue at a pole of order n. Residue at z equals to a is equals to 1 by n minus 1 factorial in bracket differentiation n derivative n minus 1 times with respect to z of z minus a whole power n f of z. Now C residue at a pole z equals to a of any order. Residue of fa is equals to coefficient of 1 by t. For using this method, given problem, we expand the given problem. Just like z cos 1 by z, we expand this term and multiply by z, and the coefficient of 1 by z is the residue. Now D, if residue of fz at z equals to infinity, then residue is equals to limit z tends to infinity minus z fz. Here another method for finding residue, Cauchy residue theorem. In this theorem we find the integral of fz dz, and using residue we find this equals to 2 pi I summation I equals to 1 to up to n residue z equals to ai. Let's do some question on this cases. Here f of z is given. Here you can see poles are 1, 2 and 3. In this question we find the residue at the pole 1, 2 and 3. Here using here residue at z equals to 1, limit z minus 1 f of z. Here we use this first case. Here z minus 1 limit z tends to 1 into f of z. F of z is z square divided by z minus 1 into z minus 2 z minus 3. Now this z minus 1 is cancelled out by this. Putting z equals to 1 we get here 1 by 2. And similarly for residue at z equals to 2, limit z tends to 2 z minus 2 into z square divided by z minus 1 into z minus 2 z minus 3, and this cancel out by this, and putting z equals to 2 we get residue minus 4. And similarly for residue at z equals to 3, here z minus 3 z square divided by z minus 1, z minus 2 into z minus 3, and this is cancelled out by this, or putting here limit 3, we get here 9 by 2. Now let's do another question on Cauchy residue theorem. Find the integral around mod of z equals to 2. Here you can see poles are 0 and 1 and order of 1 and 2. Now finding residue at z equals to 0, limit z tends to 0, z into f of z. Now putting here fz, we get here, here you can see this is power 2, so we use here this case, this b case, residue at a pole of order n. Here n is equals to 2. Now using this formula, for this, for in first case, we put here this. Now putting z tends to 0, we get here equals to 1. Now in this case we use that formula because this is a pole of order 2. Now limit z tends to 1, d over dz, here 1 by 1 n minus 1 is given, that's why 0 factorial is equals to 1, and this will equals to this, and here n minus 1 is here, and this become 2 minus 1, and this also, and we can write here d over dz of z minus 1 whole square f of z. Now limit z tends to 1, d over dz of z minus 1 whole square e raised to power z, z into z minus 1 whole square. So this is, and this is cancelled out by this. Now let's do their differentiation. Now putting limits equals to 0. Now using here Cauchy residue theorem, residue at z equals to 0 plus residue at z equals to 1. Now 2 pi I into 1 plus 0 and equals to 2 pi I. Now let's do another question. Find the residue at z equals to 0 of z cos 1 by z. Now expanding cos 1 by z to z square 2 factorial z square plus 1 by 5 factorial z raised to power this is 4 factorial and this is z raised to power 4 minus 1 by 6 factorial z raised to power 6 plus up to so on. Now multiplying this z, we get here z minus 1 by 2 factorial z plus 1 by 4 factorial z raised to power 3 minus 1 by 6 factorial z raised to power 5 up to so on. Now residue as z equals to 0 is equals to minus 1 by 2 fact 1 by 2 coefficient of coefficient of 1 by z. Now let's do another question. F of z is equals to z cube divided by z square minus 1 at z equals to infinity. Now first of all we need to expand this term. So taking common here z square, and this will cancel out by this. So we can write this like that term minus 1 here. Now expanding this, so this is z square and this is z raised to power 4 up to so on. Now multiplying by z, here we get this. Now using here residue at infinity, which is equals to minus coefficient of 1 by z, now equals to minus 1. Now let's do another question. Determines the poles and residue at each pole of the function f of z equals to cot z. Now we can write f of cot z cos z divided by sin z here. Now putting denominator equals to 0, here we can write here z equals to n pi, where n equals to 0 plus minus 1 plus minus 2 up to so on. Now finding residue of fz at z equals to n pi. If we put here z equals to n pi in fz, it's becomes 0. Denominator term becomes 0. So we use here this formula. Now differentiate denominator term, we get residue at z equals to n pi equals to cos z divided by, here differentiation of sin z is cos z, so equals to 1. Now for solving contour, we have two theorem. Theorem 1, if AB is a arc of the circle between theta 1 and theta 2, mod of z minus a equals to r, if limit z tends to a, z minus a of z equals to k, here k is a constant, then limit r tends to 0, integral of ab fz dz equals to I theta 2 minus theta 1 k. Now another theorem, If AB is an arc of the circle of mod z equals to r between theta 1 and theta, theta is lie between theta 1 and theta 2, if limit r tends to infinity z fz equals to k, here k is a constant, then limit r tends to infinity integral ab fz dz is equals to ik theta 2 minus theta 1. Now evaluation of integral of type minus infinity to plus infinity fz dz, where fz has no pole on the real line. Now consider a closed contour in the upper half of the in the upper half plane and the real axis from minus r to r. Then integral fz dz equals to integral of semicircle fz dz. Here this symbol represents semicircle. Integral of semicircle fz dz tends to 0 as r tends to infinity. So f of z dz of closed curve is equals to minus infinity to plus infinity f of z dz. Here this is equals to 2 pi I sum of residues of fz inside the contour C. Now let's do some question on this topic. Given as integral limit 0 to infinity dz divided by 1 plus z square. Here you can see poles are z equals to plus minus I. Here this is a diagram of this question. Now using here evaluation of integral of type integral minus infinity to f plus infinity fz dz. Plus first we need to find limit fz tends limit r tends to infinity of fz, then limit r tends to infinity of z divided by 1 plus z square 1 by is equals to 0. Now limit r tends to infinity of semicircle fz dz is equals to 0. Hence integral fz dz is equals to minus infinity to plus infinity dx divided by 1 plus x square. Let's find integral fz dz using residue theorem. Now residue at z equals to iota limit z minus iota f of z. Now putting the value of fz and taking limit z tends to I. this cancel out by this. Now putting z equals to iota, we get here this. Here you can see in this diagram the positive value of y is here, so minus iota is outside the contour, so for this residue is 0, hence integral fz dz is equals to 2 pi I into sum of residue, which is 1 by 2 iota, and this is cancelled out by this, equals to pi. So minus infinity to plus infinity, dx divided by 1 plus x square equals to pi. Now this is now using here 0 to infinity limits, so this become this pi by 2. Now let's do another question. In this question we need to prove that integral dx divided by 1 plus x square whole power whole square equals to pi by 4, and this is given as now first of all fz equals to 1 by z square whole square. We need to put in the given value x equals to z, so fz becomes this. Here pole becomes this of order 2. Here z equals to iota lie in upper half of the semicircular plane, but minus iota does not lie. Now fz tends to 0 as z tends to infinity. So integral of semicircle fz dz tends to 0 as r tends to infinity. So integral fz dz is equals to plus minus infinity to plus infinity dx divided by 1 plus x square whole square. This term becomes 0 as r tends to infinity. Now we need to find the value of this integral. So using here residue theorem, 2 pi I residue at z equals to iota. Here you can see this is the order of 2, pole is the order of 2, so using here d over dz z minus iota whole square divided by this term. Now we can write here z tends to iota d over dz 1 by z plus iota whole square. Now on solving we get here pi by 2. Now putting the value pi by 2, here pi by 2 is equals to integral minus infinity to plus infinity d of x 1 plus x square whole square. Now we can write here 0 to infinity dx divided by 1 plus x square whole square. Here now another topic is integration around the unit circle. Of type integral 0 to pi limits f of sine theta cos theta d theta. Here z is equals to r into e raised to power iota theta. If r is equals to 1, so z equals to e raised to power iota theta. Now here sine theta is equals to e raised to power iota theta minus e raised to power minus iota theta divided by 2 iota. We can write here in term of z minus 1 by z. Similarly, for cos theta, we can write here this. Here you can see z is equals to e raised to power iota theta. So dz is equals to this. So d theta is equals to dz over iota z. Here this term is z, so we can write here z. Now integral becomes z minus 0 raised to power minus 1 divided by 2 iota comma z plus 0 raised to power minus 1 divided by 2 dz divided by iota z. Here we convert d theta into dz. Now let's do a question on this topic. D theta divided by 1 plus a cos theta. Here a square is less than 1. Now using here cos theta is equals to 1 by 2 z plus 1 by z. Putting here dz is equals to d theta is equals to dz divided by iota z. Now on solving we get here this value. Now let this term I first of all we solve this equation. Here z is equals to minus 2 plus minus root 4 minus 4a square divided by 2a, and we get here this value. Here there are two zeros of z, so let one is alpha is equals to minus 1 plus root 1 minus a square divided by a, and another beta is equals to minus 1 minus root 1 minus a square divided by a. Here you can see in the given condition you can see contour may be in the positive y axis, so positive real axis, so beta is outside the circle, so we used this value. Now I is equals to, here we need to find this value, so we need to find residue. Sorry for this. This is 2 pi I limit r tends to alpha. Now 2 pi I limit r tends to alpha. Here there is no. Here we can write here z minus alpha divided by z minus beta into z minus alpha. Here this is cancelled out by this term. Now we can write here now putting the limit, we get here alpha minus beta. Now first of all we need to solve alpha minus beta. Here alpha minus beta is equals to, this term is 1 minus 1 is cancelled out by this, so this become this. Now putting the value of alpha beta, root 1 minus a square divided by, sorry, this is reciprocal, 1 minus a square, this is cancelled out by this term, so we get this. Now putting the value in this integration, now multiply by 2 by iota into this I is cancelled out by this, so the integration become this, integral 0 to 2 pi d theta divided by one plus a cos theta. Now another topic, Jordan's lemma. If fz is analytic, expect at a finite number of singularity. If fz tends to 0 uniformly as z tends to infinity, then limit r tends to infinity, integral of semicircle e raised to power iota mz fz dz equals to 0. Here m is greater than 0. Now let's do a question on this topic. Integral 0 to infinity cos mx divided by x square plus a square equals to pi by 2 a into e raised to power minus ma. Here m is greater or equals to 0 and a is greater than 0. Let f of z is equals to e raised to power iota mz divided by z square plus a square. For like cos sine term, we use here exponential for solving this type of integral. Here poles are plus minus iota a and their diagram is this, minus r to r. Here minus a iota is lie outside and plus iota is lie inside, so using residue theorem we find the value of f of z dz. Here putting this sorry, here is also fz. Now sorry, limit z tends to a iota to z minus a I into e raised to power I mz divided by z plus ai into z minus ai equals to on solving this we get here pi by a raised to power minus ma. Now using here Cauchy residue theorem, we get this value. Now, taking real part and imaginary part separately, we can write here cos mx squared sin mx divided by x square plus a square dx equals to pi by 2 e raised to power minus minus ma. Now comparing both sides, here we get this value. Now we need to 0 to infinity cos mx dx divided by x square plus a square value. So we convert this integral into this by multiplying 2. So we get this. Sorry, this is left. Now let's do another question. This is given diagram. We need to prove that integral 0 to infinity sin mx divided by x dx equals to pi by 2. Here direction of contour is given. This is semicircle 1 and this is semicircle this is semicircle 1 and this is semicircle 2. Here this is minus r and this is minus small r, and this is 0 and small r capital R. Here now let f of z equals to e raised to power iota mz divided by z. Here you can see z equals to 0 is a simple pole. Now using here Jordan lemma, integral fz dz equals to minus r to r limit f of x dx plus integral of first semicircle fz dz plus integral r to capital R f of x dx plus integral of second semicircle fz dz or equals to 0. Now putting here f of x and f of z plus small r to capital R limit now plus here as limit r tends to infinity and small r tends to 0, see capital R tends to 0 according to Jordan lemma. So we can write here minus infinity to plus infinity e raised to power iota mx divided by x dx equals to minus limit r tends to infinity e raised to power iota mz cr divided by z dz. Now for this type of question we used here mod of z equals to r and z equals to r e raised to power iota theta and dz equals to iota r e raised to power iota theta d theta, and taking limits from pi was sorry taking limits 0 to pi, we take limit according to the direction of curve is given. Here we take here limit pi to 0. So minus infinity to plus infinity e raised to power m iota mz divided by z dz equals to minus limit from pi to 0. Now limit r tends to 0 e raised to power iota mz divided by z dz. Now using this value we get this, now using the value of z and dz, and this is limit r tends to 0. Now this become this and divide by this value, this is cancelled out by this value. On putting r equals to 0, this value become 1. On integration we get iota pi, as this is iota is left. Now comparing imaginary part of e raised to power iota mx divided by dx, we can write here, we take here only imaginary part because there is a imaginary part available, real part equals to 0. So sin mx dx divided by x equals to iota pi. Now we need to prove this, so we can write here this. Now few this is important theorem. If integral 0 to infinity limit is given of integration of cos x square dx, so we can write this, and this equals to 1 by 2 root pi by 2 by integrating over a quadrant of a circle. This is for quadrant of a circle. Thank you.